In recent years, it has become established that bird tails have important effects upon their flight. In contrast to birds, relatively little research has investigated the aerodynamic functions of a bat's tail membrane, although previous authors have hypothesized that bat tail membranes perform similar aerodynamic functions to bird tails. Empirical tests of a bat tail and aerodynamics have yet to be undertaken. In this presentation, I'll explore the research article, A Potential Role for Bat Membranes in Flight Control, conducted to study the function of a bat tail using a model based on a brown long-eared bat. The tail membrane is an extension of the skin between the hind legs, often incorporating the tail vertebrae. The morphology of the tail is highly variable between species of bats and typically correlates with their foraging style. The bat model used is a simplification of a real bat in flight, representing a small gliding bat in a steady state of aerodynamic conditions. The model for the wind tunnel testing was created using detailed measurements taken from a reference specimen held at the Manchester Museum of a brown long-eared bat. The force and moment measurements were made using a 6-component force-torque transducer, which the bat model was mounted on and then attached to the mast in the wind tunnel used. Data was collected from the model with a tail membrane at a variety of leg angles and body angles, and also without a tail membrane at the same angles. 200 samples at a rate of 64 Hz was recorded and averaged to give a steady state of reading. Lift and drag levels were also recorded. Lift and drag produced by the model with the tail membrane follow similar general trends with the body angle and leg angle. As leg and body angle increased, lift and drag also increased. It is also clear that the relationship between the lift and leg angle was similar for the model with and without a tail membrane, which concludes that only body angle had an effect. The lift produced by the bat model is therefore increased by both leg and body angle, and the removal of the tail membrane had no impact. The drag was always positive and tended to increase with body and leg angle. Figure 4b shows that the drag is also increased by the removal of the tail membrane. From these results, it is shown that changes in the leg angle had a significant impact on the aerodynamic performance of the bat model. These leg angle-induced aerodynamic effects are likely to be due to two main factors: increased leg-induced wing chamber and increase in the angle of attack of the tail membrane. Both have a different impact on the bat model's aerodynamics and therefore different implications for the animal's flight performance. Data here highlights a potential role for the tail membrane in flight control. However, whether this role is a primary function of the tail or a secondary function to improving prey capture is difficult to clarify. From the results of the bat model, it was concluded that the tail membrane of many bats has a flight control function, and it can be hypothesized that bats will actively control leg position, since this will allow greater control of their flight and consequently their foraging performance. Bats will rapidly reposition their legs and tail, coincident with aerial maneuvers, and bats with the longest legs and largest tail membranes will be the most maneuverable. Thank you.